Okay, so hi everyone. Welcome to our third workshop, or workshop 2, part 2, depending on how you'd like to think of it. It's a continuation kind of our last workshop, which was an introduction to kind of why we use regressions and what they are. And last time we covered kind of the probability basics and background that are necessary to understand what a regression is. And today we'll be discussing like what a regression actually is and does when you like run one or do one. Just as a side note and reminder, next week there will not be a workshop in recognition of midterms, and then the week after we will return to working in R. Also, we do not have exercises for this week's workshop, but last week's workshops or exercises should still be available on like GitHub. They're not going to like suddenly disappear. Okay, so just as a reminder from last time, at the very beginning, I mentioned kind of there are three main reasons why economists use regressions. So the first is description, the second is causation, and the third is prediction. So description is kind of, in some sense, the most valid use of a regression, especially the kind of regression I'm going to be talking about today, which is ordinary least squares, in that in reality, when you have a regression, you are kind of describing a relationship within your data. Causation and prediction require, in some sense, telling a little more of a story, right? They require more assumptions about the way your data are distributed. They require more assumptions about the way the world works. And so in that sense, they're the more interesting things to do, but they're also, in some sense, the harder to prove. And there are certain cases in which certain things are important for causation or prediction that are not important for description and or important for causation but not important for prediction and description, and important for prediction but not necessarily important for causation and description. So moving on. So now let's move to like what regressions actually are. So the kind of goal here is, if you have your regressors X, this can be like a whole vector of random variables. You want to basically, what you're trying to do with a regression is you're trying to estimate the expectation of y with respect to x for some random variable y. So essentially, when you're doing a linear regression, what you're basically trying to do is you're trying to find the linear function of your random variables x that comes closest to approximating this function expectation of y given x equals x. And if you remember what the conditional expectation is from last time, it's essentially the mean of a random variable given another random variable. Okay, so what we're actually finding is we're trying to find the coefficients of this. So we're trying to find our beta or beta star, as the case may be, and it's actually equivalent to minimize. There's two ways to do this, or two ways to think about it. And they're equivalent. So one is finding the best linear approximation, and one is finding the best linear predictor. So in either case, you're minimizing the population mean squared error, which basically means you're minimizing the expected distance squared. And you'll find that this is actually a really common thing in kind of or a really common setup when you're thinking about all these things that went into regressions. You'll remember, for instance, like the formula for variance involved like distance squared, the formula for what was it? Oh, I guess I didn't cover necessarily some of the things that have this like same kind of like squared formula, but this is kind of for a lot. This is, I guess there's a lot of reasons. You might kind of wonder why you don't do like absolute value or to the fourth or to the sixth instead of squared, but it has to do with kind of like higher order symmetries, if I remember correctly. And we're not really going to get into that. But anyway, so either way, you're trying to solve this problem. It's basically, oh, this should say argmin here. I don't know why it's not appearing. It appeared on Overleaf and now it is not appearing when I downloaded it. Okay, so you're finding the beta that minimizes this or equivalently minimizes this, and you can like show that these two are equivalent to each other mathematically, but I'm not going to do that. Okay, so first, before we get into kind of the formula and everything, let's take a step back and recall what like joint distributions are and look like. So this is a joint distribution of two variables, x and y, or two random variables, x and y. This is like a random joint density function. And you can basically see you can just like picture this kind of as your probability distribution, right? The higher points have have higher probability. This kind of area here, or this region here, has probability 0. And you can see like there's like some maximal probability somewhere around here. And this, by the way, is the bivariate normal. In this case, you would have x and y both being normal variables. This is kind of this is a special distribution because it's completely symmetrical. There's a lot of like theory of like bivariate normal stuff that we're also not going to get into. Okay, so something else that's important to remember is kind of the relationship between joint distributions, marginal distributions, and conditional distributions. So this is just kind of a pictorial example. So here we have a joint distribution. And so here you can see this is the same joint distribution. And if you want to find the marginal distribution, what you're really doing is you're kind of projecting it against the side. You're like pushing everything to the side and creating these like marginal distributions here. And you can also think of it, and the way it's described in this picture in some sense, is that you like slice through, and then the area of the slice is essentially the height of the marginal density at that that like fixed slice. And the reason for this is because if you remember, the formula has to do with like integrating over over like dx. So if you it's really supposed to be the volume of this slice is the area of like this of the dx there, and as you take it to be for like a singular fixed x, that volume becomes that area, and that area becomes that height. So then if you want to connect this back again to marginal density or to conditional densities, what you're doing is you're taking these slices, but instead of kind of projecting it against the side, you are renormalizing them. And so you kind of have this, you take a fixed y, and then for that fixed y, you renormalize so that the sum of the area is 1. And so you now have your like conditional distribution of x given that fixed y. So now here's kind of another drawing. It's not as nice because the other one is from photos that I took of one of my textbooks, and this is something that I made in Paint. But basically, this is kind of to try and give you another way of thinking about what you're trying to estimate. So here you have maybe like your variables x and y, and they're random variables. And so if you have like kind of your fixed x equals x1, maybe you have some distribution of y that looks like this. And then you can have like the expectation of y given x is maybe this y1 here, and so on and so forth. You can see for this is supposed to be for x2, x3, and x4, right? And so then if you think about it, you should have this function of x that is this like expectation of y given x, right? And so here you can see I tried to make it so that it like kind of matched x1 and y1. So here this is supposed to be the kind of the conditional expectation of y given that x equals x1, and so on and so forth. It's important to note that there's no real reason to expect that this is, I mean, I guess there are sometimes reasons why you would expect it to be smooth, but there are cases where you might expect it to not be smooth or continuous. This is actually a little bit of an error there. It should definitely be 1-to-1, but there's no reason that you would expect, there's no reason that you'd expect this function to be something that you can kind of like easily describe. In the sense that like there's kind of a set of functions that we know very well how to describe using basic functions, right? There's all the polynomials, there's like sine and cosine, but there's also a lot of functions that we don't know how to describe as succinctly. So actually like the normal distribution is actually one such function, but there's like functions that you may have heard of like the beta function or the gamma function. And in general, these are functions that you might not be able to kind of easily think of what they're supposed to look like. So what we're actually trying to find is this linear approximation of this function, right? So you're trying to find this like closest linear approximation to this function. I would like to note here that when we say linear, it needs to be kind of like linear in terms of like these random variables, but as you may recall from one of the earlier slides, you can have your random variable x be a vector, and you can actually have functions within that. So for example, you can do, it has to be linear in coefficients. So you can't have, so all the coefficients that you estimate have to be linear, but you can't have like this be, but you can, instead of doing x, you could have like an x squared here and regress on x squared. So in some sense, so that's why I was saying that there's kind of functions that, that's why I'm saying that it's important to think about functions that you can and can't kind of easily describe, because it is, for instance, possible to regress on x squared, or log x is really common to regress on. So here's kind of like when you're thinking about an actual regression, what you're trying to do is you're trying to find this like purple function here using some data. And here I've just kind of like drawn a bunch of like random blue points in. They're supposed to represent data points, and they're supposed to kind of match what the thing looked like earlier, but, or what the conditional expectations looked like earlier, but, or densities, but yeah. Anyway, so you've got some data, and so then you're trying to find the line of best fit for that data. What you're trying to get, what you want is that line of best fit is supposed to approximate this line as closely as possible. Now, it is entirely conceivable that you might not have such a great approximation, right? This might occur like if you have a bunch of outliers in your data, if you don't have that much data. All of those kinds of things are reasons why, you know, you might be concerned about the quality of your kind of sample approximation of the purple line. Okay, so going back to what these formulas are. So we have these two conditions, right? That like we have beta star such that it's minimizing this. And I'm not sure whether, I think I'm still staying. And so you've got beta star such that you're trying to minimize this. And as long, and basically you have this rule that as long as this like expectation of x transpose is invertible, you have this like unique solution. That basically occurs whenever x is, whenever you have like no perfect multicollinearity, or basically you need your variable, you can't have your variables be able to add up to a constant, or have kind of like a set of constants that will enable your variables to add up to a constant. Not entirely sure what happened to Zoom, and I hope it's still recording. If not, I guess I'll just go back through this again later. Okay, so when you have this, you can actually also write down this as a linear model instead, where you have like y equals x transpose beta star, where again beta star is these like coefficients, and u is this kind of like error term. And essentially the rule is that your residual. And the rule is basically that like x and your residual have to be orthogonal. So when you have this kind of like unique solution, that's great and all, but like we want to think of like what does this actually mean? What does this actually like look like or imply about what beta is actually telling you? So the kind of simple example with like one regressor and a constant, you'll have kind of this linear model, and basically you can find that your coefficient on your random variable is going to be the covariance of your random variable with your regressant over the variance of your regressant. Wait, is that correct? Yes. No, that's not. That should be the variance of your random variable. This should be a W here. Sorry. And so, and then here, what you have is that your constant should basically be like the difference in the means, or the difference in the mean minus like this, the slope times the other mean. So basically what this alpha star means is that it's equivalent if you just like demean all your if you demean all your variables first and then rerun the regression, it won't affect like your actual values. And remember, this is supposed to be a W, not a. All right. I'm not entirely sure how to. Okay. This should be. Never mind. I'm going to do it on that in a moment. Anyway, again, this is supposed to be a W, not a Y there. Okay, so that's what it looks like with one regressor. And this kind of makes sense, right? You're basically looking at like some sort of relationship between what your like two variables are, kind of scaled by how much those variables vary. Okay, so but like what about if you add another regressor? So this is really common, right? It's normally you don't want to just like regress two variables against each other. You'll hear people talking about control variables all of the time. Those are adding additional regressors. So what this does is you can you now have these kind of two different models that you're comparing, right? And you can get these, and you can get kind of directly compare what the coefficients from these results are. By the way, if you're wondering what like the formula is for gamma star L, you can find that. I believe it's essentially the same as gamma star S, in that it's like the covariance over the variance, but there's another 1 minus the correlation of the two variables underneath, but that's not really relevant. Anyway, so the point is, it's important to note that what these two regressions are telling you are two different things, right? The first one is telling you the relationship directly between two variables. The second one is telling you the relationship between essentially three variables, or in kind of one direction. And so normally when you're talking about when you're talking about interpreting a regression causally, you'll talk about this term here as kind of your as your like omitted variable bias, right? So this means that you have a variable that like affects both y and w that you're not including that you really should be. However, it's important to note that there might be occasions where you don't really care so much about an omitted variable bias, or maybe you know that you're not going to be able to control for the omitted variable bias anyway. So like it's good to know what this looks like so that you know what the kind of direction of your bias should be, but it's not always something that like in particular if you're doing something descriptive, right? If you just want to know how or not, or if you just want to know what the relationship is between like parental income and like the children's income, there's a lot of omitted variables if you were going to just regress like children's income on parents' income. But maybe for the moment you don't care about those so much. Maybe for some reason you really just want to know what this like generational thing looks like. And so in that case, it's like a little weird to call it an omitted variable bias, because it's not because like bias kind of has like a negative connotation. But in a lot of cases, you do care a lot about omitted variable bias. And in a lot of economics is really more about kind of figuring out the relationship between things, but figuring out a causal relationship usually. Or well, not usually. I feel like most things that I've read have had to do with causal relationships, but I guess maybe that's too small of a sample, right? And so in that case, but there are also a lot of occasions on why it's important to know kind of what this looks like. But there are also a lot of occasions where you don't know, where for some reason you know that there's a variable, but you may not be able to measure it, right? So if you're looking in at kids like scholastic achievement, maybe you don't have some measure for innate ability. You kind of like just have like their like final test scores and like their parents' level of education or something like that. I don't know. For whatever reason, your data might be limited. And in that case, it's really good to know this, because if you know kind of more or less how your variable that you know that you can't measure is related to your outcome variable. So if you have some idea of like the sign of this delta, and you know more or less how this variable is related to the variable that you're regressing on. So like, you know what this kind of, what this covariance, if you know kind of like what this, what in particular the sign of the covariance, I guess, then you have some idea of like which way your bias is going. And that can be really helpful. The kind of the constant term is like generally less informative, and we just generally care about it less. Okay, so but if we have this formula, like what can we actually do with it, right? Like that's not necessarily super helpful. Our whole problem is like we don't know what the sample, we don't know what the population really looks like. So we go to the sample, right? So one kind of easy thing to do is you just take the sample analogs, right? You have this like expectation, so you take the sample mean, right? And that actually is the ordinary least squares estimator. You can also arrive at this because if you begin with like the best linear prediction function, which was way back over here, you can also kind of like start by taking the sample mean there, and you get this formula, which you'll find that this is the same beta hat. So this is kind of this. So this is in essence an estimator of beta star, which is your approximation to the function that you actually care about. So a bit about residuals. So for any object, once you have your data and you've done your regression, right? You have your beta hat. You now have kind of two values, right? You have your y hat, which is your like fitted value, and you have your actual value from your observed data, right? Because presumably you're doing all of this with observed data. Quick question. I'm not entirely sure what happened. Did I just like totally disappear? Okay, I'll just keep going, and I'll check afterwards and hope that the recording turned out okay. Okay, so you then can have like this like estimated idea of your residual. Remember that like in your model form, you had your residual, which is kind of like an error, but it's really more like the part of y that like isn't explained by x is another way to think about it. And so here you have your estimated residual. So your ordinary least squares estimator actually minimizes the sum of the squares of the residuals. And so what this does, by the way, if the video turns out totally okay, and you just wonder why I keep checking whether it's turning out okay, that's because there's like weird things going on with my computer. Anyway, so yeah, so that's why part of why it's like ordinary least squares. You're taking the line that makes the least that makes this like square value the smallest. Okay, so about r squared. So you'll hear a lot about r squared, maybe less now, depends on who your professor is too. But basically, so the definition of r squared is basically kind of, it summarizes how far the residuals are from like the line. And you'll also hear about like adjusted r squared, which basically it adds like a degrees of freedom adjustment. So there's like a times n over n minus dx or something like that, which is just like an adjustment for degrees of freedom, which is a concept you'll get into in your stats class. Anyway, so here's the formula for your r squared. And so people do talk a lot about r squared. I guess maybe my personal econometrics professor had a lot of opinions on how much people thought about r squared, and mostly that they were too much. But something that's kind of important is that r squared is like really important for prediction, right? If you're trying to predict y, you really do care about the fit. But it's not necessarily as informative for descriptive and causal analysis. And kind of the degenerative example of this is if your relationship between your variables is actually 0, right? If x really is like completely independent of y, and your gamma should be zero because like the covariance equals 0, right? Mechanically, your r squared is going to be is going to be 0, which like is not that helpful, right? Like but it is important on the other hand to know that the gamma star is 0, and it's helpful to know that, and that is actually kind of almost surprising in and of itself in certain cases. There are cases where it's not surprising, but you know, it is sometimes surprising when you do have like the relationship turns out to be like null. And there's some other cases where like it's weird, but because of that, there are ways in which r squared is very important for prediction and is less important in some ways for description and causation. Not to say that it's like not important at all. It is a measure of how good your approximation is, but it's not the be all and end all of like the quality of your model. And also focusing too much on it can lead to kind of like attempts at overfitting, which is also like not helpful. Okay, a comic from XKCD, because why not? Lighten this a little bit. Okay, yeah, so I included this comic because something that's really important to consider about linear regression is that it's really all fundamentally based on probability, right? So that is why you kind of have this like very and that's kind of where I guess p-values begin to come in, because what you're really saying when you're running a linear regression and you have like a p-value of 0.05 is that you're like confident that this is like a real relationship that's different from 0, right? But you're not saying that like it definitely is. And when you've got your and even when you're kind of approximating your function of conditional means, even then that is a conditional expectation, right? And that's not everything. That's not telling you all the information about the variables. That doesn't mean that there can't be outliers. It does mean that it is kind of what you expect to occur in some sense, but in some cases, if you recall, there are ways in which the expectation is not necessarily the most informative thing about a variable. Anyway, moving on to interpreting regressions. So like, it's all great to know what goes into a regression because that can help you think about regressions when you're interpreting them, and that can help you think about kind of regression design. But you know, it's really just sometimes more useful to just like know how to read a regression table. Okay, so this is an example from a paper by Professor Burstein, who's a professor here at UChicago, and two other authors, Gonzalez and I forget the third. And basically, this paper is on like misperceived social norms. They went to like it's an experiment. It's kind of experimental. They like went to Saudi Arabia. They got people. They like asked them like what they thought. They asked them about their willingness or their belief in the appropriateness of women working outside the home. And then they asked them what they thought everyone else's belief about the appropriateness of this was. And they found that there was like a misperception that people were more willing, or at least said that they were more willing to let their wife work outside the home. And then they thought that other people thought that that would be bad. And then they had like this like thing where they like randomly told people whether they randomly corrected this misperception, and then also kind of like gave this opportunity to have like their wife sign up for like this job matching service. And then there's kind of like longer term outcomes about like interviewing and stuff or whatever. Anyway, but basically here you can see what the regression table is, right? So here on the regression table, the first thing to keep in mind is that you want to make sure that you know what the regressand is and the regressors, right? So in a regression table like this, where it just has like 1, 2, 3, 4, that means that they all have the same outcome variable, and they're just like different designs, right? Sometimes that'll be different variables, sometimes that'll be like information conveyed down here. And then what you're actually regressing on will be included on the left. And then kind of in the middle, what each of these numbers are, like here, whoa, that's a new highlight, and here, these are all coefficients. So those would be kind of like your gamma stars, or not gamma stars, gamma hats, your estimates of gamma stars, so to speak. That is to say, the relationship between your regressor and your regressand. And this, what they're actually regressing on is like whether or not people like they signed up for like this job matching service, which apparently was costly. I forget exactly how. It's been a while since I've read the whole paper. Anyway, and then here what they're reporting is their constant. And again, just as a reminder, you really care much less about like your constant than you do about like everything else. So then underneath, in this case, in the parentheses, I believe they have their p-values reported. So essentially a p-value is telling you the chance that you get that kind of, that coefficient if the actual coefficient is 0, right? So when you have a p-value of 0.5, you're saying you're 95% certain that given the result that you got, that you wouldn't have, that it's not 0. So here, it's not always the case that the parentheses will be p-values, by the way. Sometimes they're like standard errors or standard deviations. Sometimes they'll even report the variances, all sorts of delightful things. Anyway, so in this table, I'll actually move to the next slide because that shows a little more. So these regressions essentially represent kind of this kind of model, right? So here, like y would be like whether they signed up for the service, t would be whether or not they were treated, and then x here are like various sets of control variables. By the way, this like inference robustness section, that has to do with like lots of fancy computational ways to like find additional, to like think about p-values and like think about how likely it is that you actually get this result, given that that's not the real result. And we're not going to discuss this. Down here, you'll often have these kinds of like check mark things where it'll tell you what else is included. So here it's saying that this first model doesn't include any of these, and then this model only includes the session fixed effects. This model includes session fixed effects and controls for baseline beliefs. This model includes both of those and also controls. They list out what these variables actually like include elsewhere, but it's also not particularly relevant for like our ability to kind of understand the basic idea of this table. And so those would all kind of go into like this x variable over here. Here x is like a vector, and t is the variable that we care about, right? So here, this would be kind of our b hat of b and our alpha hat of alpha. And actually there's no gamma or x because you don't have like these extra control variables. Usually you don't report the coefficients for all your control variables because there are a lot of cases where you'll have like even hundreds of control variables if you're like running a panel regression. But you know, it's not necessary to like constantly be reporting the coefficients on like age and race, for example. Right, so n here is the sample size that each regression is being run on. And here again, you have your like r squared. Yeah, so that's kind of like a very simple example of a table. This is a nice table for us to start off looking at because it is from an experiment, which means that they kind of just ran an OLS. They ran like a basic linear regression so that you can see what happened. Okay, this is another example of a regression table. This one is about the kind of, incidence of, the starting times of like civil wars. And it basically is kind of looking at the relationship between these variables in a given year, in a given country, and like the likelihood about like a civil war starting the next year. So like once again, you can see that you've got these different, you've got 1, 2, and 3 for your 3 different models. Here, they're looking at a lot of variables at once because this is kind of a more exploratory, like we want to see like what of these variables actually matter kind of paper. And so you can see that they have that, like, for example, this one doesn't have income and land inequality. This one just has income inequality. This one just has land inequality. And so this tells you like what variables they're actually including for each of these. Something about this one. So in this one, it's like, if I remember correctly, it's like a simple OLS. You can interpret these as like basic coefficients, like just like the slope of the line, right? Here it's a little more complicated. They're actually running a logit regression because their outcome variable is like a 0 or 1 always. And so there's some reasons why you would run a linear regression for that, and there's reasons why you wouldn't. One alternative is the logit regression. But what that means is that these numbers aren't like necessarily direct coefficients, but are odds ratios. Here they've got their standard errors in parentheses, not their p-values. And you can see at the bottom, they've got their n, they've got like the number of like wars that are actually within their like data set, because n is just like the number of observations, like countries and years, right? That's not necessarily if you've got a lot of countries and years, but like maybe the likelihood of war is just like really, really, really low, then like, you know, maybe you still don't have like a good data set to be basing anything off of. So because this is a logit regression, they have their pseudo R squared and their log likelihood, as opposed to just like their R squared. Something that is important for kind of just generally when looking at regression tables is that there's like, you know, a philosophical debate about kind of the role of like the little stars, right? That indicate significance. Some people think that there is too much emphasis placed on the little stars and that it's better to not have them. Others feel that like having the stars make the table a lot more legible and like help you focus help readers like focus on what you actually want them to like look at. Personally, I'm in favor of legibility of tables, especially because like these are both kind of relatively simple tables in terms of like the number of things that they include and like everything. So it is, I personally find it like nice to have stars. And besides, people are still going to like calculate your p-values anyway, or expect you to report them. You know, so it's not like it's a secret whether or not your variables are significant. By the way, if they don't report p-values, if they just report standard errors or variances, you can kind of compute if it's there's a computation, there's like an easy kind of like division that you can do to check whether it's actually significant. I remember it from I think I remember that you're supposed to divide the coefficient by like the variance, and if it's approximately greater than 2, it's like significant at the 5% level or something like that. I forget exactly. I think that's, yeah, I think it's that. So if you divide, but here these are like standard errors, so I don't fully remember. Anyway, so I think so that's more or less kind of the goal of what was to be covered for this meeting. So like here's another comic from XKCD. I'll give you a moment. I'm not about to read a comic out loud to you guys. This is just the first part, by the way. This is one of their longer comics, so like anyway. So yeah, this whole comic basically refers to a concept that you probably already heard of, known as p-hacking, where you kind of just like run regressions over and over and over again until you find something significant. Yeah, so again, this goes back to why it's important to remember that this is all probabilistic, right? Because there is a chance that you will just like randomly find something significant. There's also, by the way, a chance that you find a null result when you're not supposed to. You know, those both exist. And it's important to keep both of those in mind when you're exploring your data and when you're doing research. And as a rule, it's generally good practice to report all of your data manipulations and regression results, even if they're all like in appendices or whatever, as kind of like demonstration that you're not p-hacking. This is also why it's beneficial, by the way, to do robustness checks, which are basically when you kind of run different regression designs or use like a different data set or subset your data in different ways to show that it's not being driven by a particular portion of your data or something like that. So anyway, that was just kind of like a brief overview of regressions are and do, and I will stop the recording now. And if anyone has any questions, we can go over them.